All right, hello, Physics 4a. So a few things. We've got our first exam coming up next week, a week from today, and I'll send out a practice, not a practice exam from the physics point, a practice exam from all the procedural stuff. Where do you find your exam? It's going to be in Canvas. How do you upload it? You have to make a PDF of it and you upload it in Gradescope. So all of that stuff, we'll do like a practice run so you're not learning all that stuff for the first time on exam day, right? We don't want to do that. And then I'll also try to update the Canvas site with all the links for meetings and things, so you don't have to search through all your emails to find the links for the meetings. Hopefully they'll all be in one place on Canvas. And then what else? And then we have a review session / office hour, whatever you want to call it, right after class today. So if you have if questions, issues on anything you want to go over, we'll do that today after class. We'll just stay right in this meeting. We'll just keep it going. Okay. All right. Okay. I can't help you with the lab, but all right. And then it probably is best if, because the class is so big, as much as I would like to see all of you, it's probably best if you don't have your video on, if you mute your video, because it makes the link go. If we all had our video on, it would really slow down the connection. And then, although it would be much more enjoyable for me to see all of you and see if you were getting things and stuff, but trust me, it would with 40 or 50 or more. Usually, we have a lot more than that. It would really slow down the internet connection with all the video on. Okay, so let's get started. And we'll start out with a one-dimensional kinematics problem, and then we'll move on over and try to, oops, try to take this to a two-dimensional problem next. Spilled on my keyboard. Okay, crisis avoided. All right, here we go. So we're going to attempt this problem here. We've got a test rocket being launched vertically upward, and it starts out underneath the ground, and there's some kind of a catapult that gets it so that when it hits ground level, it's going 80 meters per second. And at that instant, the engine fires, and it has a constant upward acceleration of 4 meters per second squared until it gets to an altitude of 1,000 meters. And that's when it runs out of fuel, and the engine turns off, and it goes into free fall. So the acceleration is only the acceleration of gravity. So it wants to know for what time interval is the rocket in motion above the ground? What's the maximum altitude? What's the velocity just before it hits the ground? All of these things. So we'll think about this for a minute. Maybe I'll give you a minute to think about it. But we've got, so think about what's going on and how you would approach that problem. Right, it starts out at ground level with some initial speed, and it accelerates at a certain rate for the first 1,000 meters. And then something changes, right? And there's a different acceleration for the rest of the problem. So what has to happen here is that we have to split this up into two problems, right? Because our kinematics equations are only good for constant acceleration. And there's constant acceleration for the first 1,000 meters. And there's constant acceleration after that for the rest of the problem. But there's not constant acceleration from the beginning to the end. It changes in the middle, right? So we split it up, the first 1,000 meters and everything after that. And we can use kinematics equations for the first part. We can use it for the last part, but we can't go from the beginning to the end with one set of equations because the acceleration changes in the middle. It's not constant from the beginning to the end. So we'll break this up into two problems. Okay, so the first part of the problem, up to 1,000 meters in height, A is equal to 4 meters per second squared up. And for the second part of the problem, it's 9.8 meters per second squared down. And I always like to make these charts. So I've got part 1 and part 2. And I'm going to have y initial for part 1, y final for part 1, my v initial for part 1, v final, acceleration for part 1, and time. And I'll have the same things, y initial and y final for part 2, v initial and v final for part 2, acceleration and time. And before I can fill these in, what do I have to do? Define the origin. That's exactly right. And your positive direction. So I'm just going to go with the ground here as being y equals 0 and up is positive, right? Good. So if that's what we define, then see if you can fill in the table here. Let me go back up to the problem so you can see what the numbers are. So they're telling us what the acceleration of the rocket is in part 1. It says that when the engine fires, the rocket accelerates upward at 4 meters per second squared. So that's the combination. That's the rocket's engine and gravity. That's everything acting on the rocket. I think it's easiest to use the chat box. I monitor it pretty closely for responding. Okay, so you understand with what's happening here, right? The rocket at ground level already has some velocity when the rockets kick in, when the engines kick in, and it goes with constant acceleration for the first 1,000 meters, runs out of gas, but it had some speed, right? So when the rocket shuts off, what's going to happen? It's not just going to stop. It's got some motion in that direction. It's going to keep going until gravity causes it to stop and then come back down. So we're given the speed when it comes out of the ground, right? So that's the initial speed. So where does it start? It starts at ground level, y equals 0. And where does it end, part 1? 1,000 meters, yes. Yeah, in the question, they give you, they have to tell you, yeah, I don't know why they told you negative here. Here they said, they used the word upward. So I would have, if they used the word upward here, they should have just said downward here, not negative. But here they used positive, so here it would be negative. I think the way I would have worded it, if I put upward here, I would have put not negative, I would have put downward, but this is the way it was worded. So starts at y equals 0, ends up at y equals 1,000 meters. It had an initial velocity of, what was it, 80 meters per second. Final velocity, we don't know, but maybe we can figure it out. And we know the acceleration. It's upward. You don't have to put a plus sign there. I'm just making sure we all realize that that's a positive value. Time, we don't know. How about for part 2? Where does it start? It starts where it ended part 1, right? So that's an M. Where does it end up? On the ground again, or actually the split second before it hits the ground, right? What's our initial speed? Well, we don't know, but what is it going to be? It's going to be the final speed from part 1. That's correct. Final velocity, that's one of the questions we're trying to solve for. Acceleration, we do know it's 9.8 meters per second squared in the downward direction, which is negative for us. And time, we don't know, but we could we could solve for time and v final if we had 3 other things, right? If we had v initial. So we have to look back at part 1. Is there a way for us to solve v final part 1, v initial part 2? Yes, there is. So we'll look at part 1 and we'll get the time time for part 1 and the v final for part 1. So if I'm going to get time and I don't have v initial, sorry, I don't have v final, I'm missing v final, then I'm going to choose an equation that's missing v final so I can just solve one equation and get time. And this is the equation I would use. No, the final point here, the question is, will the velocity be zero at final velocity here be zero? No, because it has constant acceleration all the way up to this point. It has constant acceleration. It's going faster and faster and faster. And then the engine stops. And at the instant the engine stops, that's where we're calling it the end of time one. But it's got a lot of speed. It's going much faster than where it started because it was accelerating that whole time, right, in the same direction as it was moving. So we plug these in, being careful with our signs. Well, everything's positive, so that makes it a little easier. But we plug in our numbers, 1,000 equals 0 plus 80t plus 1/2 times 4 times t squared. And I got t was going to be either 10 or minus 50 seconds. And we throw out the negative root and we use t is 10 seconds. So 10 seconds it takes for that to make it up 1,000 meters. Now we can use any equation we want. If we're confident in this number, we can use any equation we want to get V final, and there's the easiest one is this one. So that's going to be 80 plus 4 times 10, 120 meters per second. So now we can put 120 here. And now we know 3 of the 5 things for part 2, so we can solve for the 2 missing items. And remember, this equation, whenever you use this equation that has v squared and you're solving for v, it could be positive or negative, right? When you take a square root, it's plus or minus 184 meters per second. And of course, we know it has to be when it hits the ground, or I guess I should say the split second before it hits the ground, it's going to be going downward. And so it's going to be moving in our negative direction. This is really V final 2. I should have a 2 there. Okay. And then once you know that, you can find T2. And you just have to be careful. If the numbers are negative, you've got to plug in the negative numbers here. Just carry those minus signs along through all your calculations. Nothing too tricky here. You just have to be careful. So this is my T2 and T total. "41 seconds I got." So we found the speed and we found the total time in air. It also asked for the highest point. I'm not going to do that. You can do that for yourself if you'd like. But you can see here with these problems, they do this a lot. They'll have a car accelerating onto the freeway, and then it sees a highway patrolman and slows down, and so it asks, from the beginning to the end, how much distance or how much time or something like that. Well, you have to break it up. While it's speeding up, there's one acceleration. While it's slowing down, there's a different acceleration. You have to break it into two problems, and excuse me, your final velocity for the first problem becomes your initial velocity for the next problem, just like we did here. All right, so what I would like to do is talk a little bit about two-dimensional motion, because you'll want to probably hit some problems over the weekend with that. So let's get a little jump on that, two-dimensional motion. And what I want to do is introduce you to so this is going to be a motion diagram, two-dimensional motion diagram. But I want to show you this video first. So we'll watch the video, and then we'll come back and talk a little bit more about the motion diagram. Oops, hold on a second.
We want to analyze this projectile using a motion diagram. When the strobe light goes off, our particle is represented by that dot at the origin. The second time the strobe light goes off, our object is here. The third time it goes off, it's here. You can see that the motion of our particle is up and to the right. And the fifth time the strobe light goes off, the particle is at the top of its motion. Then it starts its way down and continues until it crosses the x-axis again. Now let's watch our projectile. Once more in slow motion.
Okay. So that's two-dimensional motion. And it looks something like this, right, on an XY chart. And what's interesting here is that if we were to sort of have a light shining straight down, or I guess let's just look at the X direction. The X direction, our object is here. If this is t equals 0, our object is here, right? And then if this is t equals 1, 2, 3, 4. Then at t equals 1, where's the x component of our object? It's here. And at t equals 2, it's here. And at t equals 3, 4, 5, 6, and it finishes up at t equals 8 there. So if we're just looking at the x, if we just look at the x motion diagram here, we've looked at motion diagrams before. How would you define, or how would you describe that motion? Constant velocity or constant speed, right? The speed is not changing in the x direction. The molecule, because we know that that strobe light goes off every time we get a dot, right? It goes off at equal time intervals. If the spacing is equal, then the velocity has to be the same, right? The speed has to be the same. So this object is moving to the right with constant speed. Well, that's what we get, right, when we project each one of these onto the x-axis. And that's because there are no forces in the x direction, right? When we throw this through the air, we're ignoring air resistance. The only force acting on our object is gravity, and that points straight down. So in the x direction, in the horizontal direction, there are no forces, so there are no accelerations, so it moves with constant speed. But if we project these over to the y-axis, and we look at what is it going to look like on the y-axis, then on the way up, we've got our particle here. Then we've got it, what happened? It shifted on me. There we go. Then it's going to be here. Then it's going to be here. Then it's going to be here. And the fourth t equals 4, it ends up right there, right? So this is a 0, 1, 2, 3, 4. And then on the way down, if we start with 4, here I'll repeat 4, 5 would be here, and then 6 would be here. And so what does that look like? That's the motion diagram for me just throwing something straight up in the air. If I throw this pen straight up into the air, it's going to have that exact motion diagram. It's going to go up, come to rest momentarily, and then come back down with increasing speed on the way down. It's going to have that exact motion diagram. So what this tells us, for two-dimensional projectile motion, we can split up the x and y. The x and y motions are independent of one another. And we can treat it like two one-dimensional problems, an x motion problem and a y motion problem. So let's do one. So you're standing on top of the same cliff you were standing on last time. What was it, 50 meters, I think, right? And you're going to throw the ball. Your well-calibrated arm always throws the ball at 30 meters per second, but instead of throwing it straight down or straight up like you did last time, you're going to throw it out at an angle like this. So you're going to launch it out here at an angle of, what should we do, 30 degrees? And what's that ball going to do? It's going to follow a path like that. And it's going to, oops, got to plug in. There we go. Don't want to run out of battery power now. All right, there we go. So it's going to look something like this, right? So let's go ahead and set this problem up. We're going to sort of pretend that because we know we can, we're going to split it up and sort of view the x motion and the y motion independently. So we're going to look at our x motion. We're going to look at our y motion. I'm going to make a little table for each one like I like to do for kinematics problems. So I've got x initial and x final. I've got my velocity initial in the x direction and my velocity final in the x direction, my acceleration in the x direction and time. And then I'm going to have the same for my y's, right? So now before I can fill in this table, what do I have to do? Define my origin and my positive directions, right? So again, it can be anywhere. The two places that make the most sense are where we start and where we end, or maybe the left. A lot of people like the bottom, lowest leftmost point. So that's what I'm going to do here. I'm going to take this as my x equals 0, and the right will be my positive direction, and I'll take this as y equals 0, and up will be my positive direction. So I'm going to put my origin at the base of the cliff, but you could have put it anywhere. Now, once we've defined that, then we can fill in this table, right? You can't fill this table in until you know what your positive direction is, until you know what your origin is, things like that. But once you know that, we can fill this in. So go ahead and fill in this table, and then we'll go over it together. Okay, have you set up your tables? Let's take a look at that. So where is it at t equals 0? What's the x coordinate? 0. And where is it at the end of the problem? We don't know, right? We don't know that yet. We don't know x final. V initial in the x direction, that we know because we can use our components here, right? So we know we launch this thing at an angle of 30 degrees, and it's 30 meters per second. So in this direction, we're going to have 30 times the cosine of 30 degrees, right? And in this direction, we're going to have 30 sine 30 degrees. So our initial speed in the x direction is 30 cos 30. It's positive, right? It's to the right. The right is our positive direction. Our final speed in the x direction is going to be the same because there's no acceleration. The initial speed, the final speed, and every speed in between in the x direction will be 30 cos 30. There's no acceleration. It's moving with constant speed. And the time, we don't know, right? If we knew the time, we could find the distance, right? If we knew the distance, we could find the time. So let's take a look at the y direction. Initially, where is it at the start of our problem? It's at y equals 50. And at the end, it's at 0. And so that's going to give us a 30. It's positive, right? That's upward. 30 sine 30, which is 15, right? Our final velocity, we don't know. We could calculate it if we know enough stuff, but we don't know it right now. Acceleration is just gravity, 9.8 meters per second squared in the downward direction, which is our negative direction. And time, we don't know. But we have enough information in our time direction. We have 3 of the 5 things and there's no zeros in there. So because we have 3 of the 5 items and none of them are 0, we can solve for the other 2. So we can use the y motion to get time. And then what do we know about the x motion and the y motion? They're linked by time, right? When the x gets to the final point and the y get to the final point, the time is the same at that instant, right? So these times are the same. So then we can plug in to get the final distance. A question about the initial velocities. We're given the fact that the initial velocity is 30 meters per second at an angle of 30 degrees. So I just redrew it here. We know it's going 30 meters per second. That's v initial. The angle is 30 degrees. So we want to know what component of that is pointing in the x direction. That's the adjacent side. So we use cosine 30 degrees. And what's on the opposite side is the y direction. That gives us our sine of 30 degrees. And to the right and up are positive. So they're both positive. Okay. So now you just plug them in, right? And you find the right equations, plug them in. You can do that, right? But I wanted to show you that you can also do 2-dimensional motion problems with this graphical approach that we talked about earlier. So with 1-dimensional kinematics problems, how did we solve those graphically? Usually we started with velocity versus time. And then we took slopes. We said the slope there had to equal the acceleration. We said the area under the curve had to equal change in position, right? So we went that route. And we could solve a lot of these problems graphically. Well, there's a graphical approach for 2-dimensional problems too, but it's using vectors. So all of our kinematics equations are actually vector equations. I don't know why we always change from vectors into scalars, but we don't have to. So v final is v initial plus at. That's actually a vector equation. And we break it up into components. We could also say, instead of x final is x initial plus v initial t plus 1/2 at squared, we could use just some position in space, right? R final, some location in space, is R initial plus V initial. My OneNote crashed. Hold on a second. There we go. We could also say that R this is a vector equation, and if we put our origin at our starting point, then we just end up with right, our origin is at our starting point. Okay, so what we want to do, let's look at this problem and see how we would approach it using graphical techniques. So we have to put, this means our origin is at our starting point. So if our cliff is here, then we would want to put our origin here. And we know our V initial points in this direction, right? And it's going to do this and land over here somewhere, right? So what we're going to do is draw it out vectorially. I'll redraw it here. Something like this, right? So V initial gives us this direction, right? So we're going to start out V initial t. V initial points in that direction. And if we multiply it by t, it just makes it a little bit longer, right? And where does the thing end up? It ends up right there, right? So our we're going to use this equation here. We're going to use R final is V initial t plus 1/2 AT squared, right? And what is 1/2 AT squared is going to end up being this vector right here. Oh, I picked the wrong place, sorry. Thought I had it right. It's going to end up being right there, right? And when we add those up, what do we get? We get our final position, R final. This is our final. And this must be 1/2 AT squared. So there we have our triangle. And then if this section in here, we know this distance is just V, and we know this angle here is 30 degrees. And we know this is V initial cos 30 degrees times time, or V initial t times cos 30 degrees, whatever you like to think of it. And so from these, and we know this, let me move this guy out of the way. We know this is our initial height, 50. And so from this, just plugging in the numbers and figuring some things out, you can solve. Now, oftentimes when you do these, you need to know some trig stuff. So one of the things that might come in handy is the law of cosines. And the other one is the law of sines. So law of cosines and law of sines are on the formula sheet that it's on my website. So if you have a triangle, I need to draw a triangle, but let me write this in first. if you have any arbitrary triangle, it does not have to be a right triangle, with sides A, B, and C, and opposite angles alpha, beta, gamma, then this is what these two work. So law of cosines is actually Pythagorean theorem for any triangle, right? Pythagorean theorem only works for a right triangle, but law of cosines works for any triangle. It's just the general case of Pythagorean theorem. So you can use whatever technique you want on the exam. So I would say that for one-dimensional motion, drawing the graphs, doing the equations, it's kind of a wash, one or the other. It's about the same, except for those few problems I talked about where you have one item passing another one or something like that. Then the graphical approach is easier. And the graphical approach here for two-dimensional problems, I think you're probably right, is a little trickier than just using the kinematics. The one case where I would say this is nice, sometimes the kinematics equations, you have to, I can't think of the example offhand, but you have to solve simultaneous equations, and it gets kind of ugly. You'll have like, you'll have sine thetas inside of equations that you're solving for something else. It gets kind of ugly, let's just put it that way. Not that it's impossible to do, but it gets kind of ugly. But if you do it using the graphical approach, it's a little easier. Sometimes you can avoid that. So I would say you're probably right. Using the kinematics equations might be a little easier. But if you're interested, try it out. See if you can do it this way. It's, it might be something you like doing. Okay, so we touched on two-dimensional. One-dimensional motion, I think we're pretty good with. You practice it, practice problems where they link things together. That's kind of nice because it tests you a little bit more. But really start working two-dimensional problems, because every time you do a two-dimensional problem, you're getting practice with the one-dimensional kinematics too. You have to understand that. And then see how the two link together, right? The key is that time is tying the two things together. So you're getting some information from the y and you're using that to solve the x, or you're getting some information from the x and plugging that in and solving the y. I like to say that physics problems, they're like little puzzles, and you start to do it and you say, oh, I know what piece I have to put in here, and I can use this equation and finish the problem. And then you say, oh, wait a minute, I don't have that piece to the puzzle. What am I going to do? And then you have to look for is there other information in the problem that's given? How can I solve for that missing piece so I can stick it into the equation I'm pretty sure I need to finish the problem? And that's what makes them fun, right? That's what makes physics problems fun. Okay, so there's our physics two-dimensional projectile motion problems, and we'll continue with those next time. So don't forget, I'll be sending out some emails over the weekend. I'm going to try and put all of the links, like I said, on Canvas, so you don't have to hunt through old emails to find links to Zoom meetings and things. And then we'll do some kind of practice test on all the procedural stuff for taking an exam, so that that's all worked out beforehand. And our exam, Friday. All right, so we'll end this recording, and we'll start a office hour / review session, whatever you want to call it, coming up next. Let's just take a few-minute break here, stretch our legs, and then we'll do our office hour. So come in with any questions you've got, and we'll get you going on that. Oh, I don't want to end the meeting. I want to, we'll stay right here in this. I just want to